Hello everyone. My name is Aparajita Sen. I am a student, PhD student at ISRO Thiruvananthapuram, India. Today I will talk about forecast of recovery R in CMB Bharat, and I will specifically focus on foreground complexities in foreground emission and the optimum range of frequency required to recover the CMB B-mode. So first, let me briefly describe what I mean by the title of my talk. What is CMB-Bharat? CMB-Bharat is a proposal for a next generation satellite, which was given by the Indian cosmological community to our Space Research Center ISRO in 2018. The proposal was given in 2018 and since then it has been under consideration with the scientists. The mission will have multitude of scientific goals, and one of the main key scientific goals is the detection of the well-known CMB B-mode. Now the existence of CMB B-mode is one of the major predictions of the inflationary paradigm, and it's the signal and it is sourced by the primordial gravitational waves which was generated during the inflation. And it will contain, once detected, we can extract very unique information about the inflationary physics and also the energy scale which was there during the inflation. The power of the CMB B-mode is parameterized by a tensor to scalar ratio, which is known as R. And all the next generation satellite experiments such as CMB Bharat and even Lightbird and Pixie, etc., are aiming to detect or constrain R at a level of 10 to the power minus 3. And CMB Bharat also has similar objective. It will constrain R at 10 to the power minus 3 with a confidence level of 3 sigma. Now, it is one of the major challenges of detecting the B mode is a very high level of foreground and also a high level of foreground. This is very apparent from this figure, where this pink line denotes the strength of the signal, CMB B mode signal, if R is equal to 10 to the power minus 3, and we can see that this signal is subdominant at all frequency ranges, subdominant to the foreground emission at all frequency ranges. Apart from this, it is also contaminated by the lensing signal, lensing signal, which is denoted by this blue line. And of course, since we are talking about detecting signal which is of the order of nanokelvin range, we will need a very highly sensitive detectors. This is briefly the instrumental configuration of CMB Bharat. It will observe the microwave sky starting from 28 gigahertz frequency to 850 gigahertz frequency. And its telescope will have a focal plane with a diameter of 50 centimeter, which will be fabricated with around 6,000 to 7,000 detectors. And the most sensitive detectors, sensitive frequency bands, will be in the range of 150 to 220 gigahertz, which can be seen from this table about sensitivity. Now, hereafter in this talk, my talk will be based on these two works. One is B-mode forecast of CMB Bharat. I've done this work with collaboration with Devabrata, who is a postdoc at IMSC Chennai. My supervisor Shaumin Basa, Jack and Tuhin Ghosh, and many others. And the second work, which the manuscript is still under preparation, and we are hoping to put it in arXiv in 1 or 2 months. This also I have done with collaboration with Devabrata, my supervisor Shaumin Basak, and Tuhin Ghosh. So the objective of our first work is to test the ability of CMB Bharat given its experimental instrumental configuration to detect the CMB B-mode signal. To make our study robust, we have considered a range of foreground components such as the thermal dust emission, synchrotron emission, spin dust emission, and faint point sources. We have also considered the effect of lensing. And since the signal is very expected to be very faint, the complexities in dust and synchrotron emissions will affect the recovery of R severely. And so to take into account that factor, we have also considered some of the complexities which can be expected from the dust and synchrotron emissions, which I will talk about in little detail in later. And also we also focus on specifically on removal of the thermal dust. So here we ask the question, how can we improve the performance of the component separation techniques? So because component separation techniques, when the signal we need to recover is so faint, so one of the main way can be to increase the range of frequency through which the foreground is being observed, especially the thermal dust is being observed, so that we can characterize its ACD or its emission spectra, and we test that if we increase the frequency range of dust observation, do we see an improvement in our detection of R. So here, this is thermal dust is empirically modeled, as we know, by modified black body spectra. And what I mean by the modified black body spectra is this is shown in this equation. So B nu here signifies the Planck spectra, the Planck function, and TD denotes the temperature at which the dust cloud or the dust grains can be emitting at, and nu naught is a reference frequency, which is around 353 gigahertz for 353 gigahertz for the dust emissions, and beta D is the spectral index through which the emission varies over the frequency. Now, this is a very simple model, and it does not take into account many of the real physical effects, such as the variation. There might be some variation in dust composition or the size of the dust grain. Even the alignment of the galactic magnetic field along our line of sight might vary, which you can see from this figure, that if we have two different population of dust clouds and they are aligned at aligned differently with our line of sight, the resultant spectra will not be just a modified black body spark spectra. It will be it will have some other modifications, and and it has been shown in the literature repeatedly that this type of dust complexities can severely affect the recovery of CMB B-mode. So in our work, we have considered three complex dust model. One is the MKD dust model, which is a three-dimensional modeling of the dust properties. In this model, what the authors do is they take into account how the dust properties such as the size and composition, etc., vary along the line of sight. The second is the TD dust model. This has been generated from three phases of HI cloud. And the third is a more physical dust model, which was proposed by Hensley and Rain. And it takes into account the physical properties of the dust grain, physical property, and also the composition and size of the dust grains. Similarly, for synchrotron model, synchrotron is normally in simple way especially for temperature and E-mode recovery. Synchrotron is modeled as a power law, which are given by this equation. It varies as by the spectral parameter beta s through the frequency, and nu naught is the reference frequency, which is 223 gigahertz in case of synchrotron. But if similarly as we have seen in dust, if the population of the dust grain are different, population of the synchrotron electrons are different along our line of sight, we will have some variations. And one of the way to model it is by introducing a frequency dependence in the spectral parameter. So this model, when it is this type of modeling is called the curve power law synchrotron model. Now, to recover the R, to actually forecast the ability of CMB Bharat to recover R, what we follow our methodologies. First, we generate the mock simulations for the CMB Bharat frequency bands. Then over these mock Chi simulations, we apply the NILC and commander methods, which are the two very different component separation methods. NILC is a blind component separation method, which does not assume anything about the properties of the foreground, and commander is a parametric form of component method. After this, we recover the bent angular power spectrum, and from this, using the maximum likelihood method, we recover the R and its uncertainty. So here are some of the results which I would like to highlight. First, we see that for our baseline model, which is the most simple model, we are able to recover R. So with 1 sigma with a good level of confidence. And so our input R is equals to 0 in this case, and it matches with the input level of R. Also, the uncertainty is given by uncertainty, which actually denotes the sensitivity of in the instrument, is around 10 to the power minus 3 to 10 to the power minus 4. This means if the B-mode, if the level of R is around 10 to the power minus 3, CMB Bharat will be able to recover the data. Next, for synchrotron complexity, for the two models that I have mentioned before, power law and curve power law, we see that NLC method can recover R within 1 sigma bias, but for commander method, we see that if we are using the curve power law model, the bias is more than 5 sigma. Similarly, for dust complexities, we see that NILC is able to perform well, even though the level of R bias increases compared to the baseline model. Still, we are able to recover this. We can recover R equals to 10 to the power minus 3. But in case of commander, that is not the case. That, as you can see, that the values of R are very large in case of commander. And next we look at the TD dust model. In the TD dust model, the first 3A dust model does not have any frequency decorrelation, whereas 3B model has about 0.2% of frequency decorrelation. So we see that in that case also, commander does not perform well, but for the case of no frequency decorrelation, commander is able to recover R equals to 10 to the power minus 3 or even lower. Now, let me come to the next part of my talk, which is, so here we ask the question, what is the frequency range for which we can ensure optimal removal of thermal dust? Component. Sorry. In 2018, Hensley and Bolt in one of their work have shown that for some cases of dust models, such as the frequency decorrelated dust model, it is better to limit the observations to relatively lower frequencies like 200 to 500 gigahertz. They had done this analysis on a single pixel of sky using a parametric component separation method. We analyze on a similar we do a similar analysis, and considering the CMB Bharat frequency channel and its noise budget, and what we find is also something similar. So this plot shows the variation of R. So input R in this case is 10 to the power minus 3, and we see if the NLC is able to recover R is given 3 different dust models, and we see that for the first 2 dust models, there is it does not, even if we include frequency, if we exclude frequency channels higher than 275 gigahertz or 340 gigahertz, it does not affect the recovery of R. The R bias does not change. It is the recovery of R is not biased. It is within the 1 sigma confidence level. For MKT dust, we see that there is a slight monotonous increase in the R bias, and this happens because the level of residual foreground especially decreases as we add frequency channels more and more. But here also it is interesting to see that once we have added a 275 gigahertz channel, if we keep adding more higher frequency, we do not see a very significant improvement. We see a similar pattern in the sensitivity uncertainty sigma, which actually gives the sensitivity of the instrument. We see that for the 1 MBB dust model, there is a drastic improvement in the sensitivity once 340 gigahertz channel is added. After that, the improvement is not very significant. Similarly, in physical dust models, we do not see any improvement after 520 gigahertz is channels. Once 520 gigahertz channel is added, and in the MKT dust model also, once the 340 gigahertz channel is added, the higher frequency channels do not improve our result. So what we conclude from this is that the thermal dust observations up to 500 gigahertz is adequate for minimizing its contamination in the recovered CMB maps, and this is also the frequency range in which the Lightbird is planning to observe. Lightbird is going to observe the microwave sky, so so this means that this frequency range is adequate for the goal for just recovering R. And other than this, we also conclude that the configuration of that CMB-Bharat can recover R to the limit of 10 to the power minus 3, and commander is not very suitable for some form of complexity such as the curve in the spectral index or frequency decorrelated dust models, etc. So that's all for my talk. I will look forward to the discussion. Thank you for listening.